Okay, good. So this week is really the sort of the resistance of the theory of sort of one-dimensional time series or one-dimensional spatial series, computational mechanics. And the goal by Thursday is to develop a representation or presentation of a process that is in some sense time agnostic. So our notion of time is sort of subjective. We get to choose this, and as we talked just briefly a couple weeks ago about what happens when you reverse time, that's what we're going to talk about today. Just being kind of honest about how we're scanning the data, and we could have scanned it the opposite direction, and what do we get out of this, right? There are these interesting properties. So that's what I want to talk about this week, directional computational mechanics. There are 2 lectures, and like I said, we needed last week's results on mixed states to even work with this. So the agenda is to review, but maybe set up the notation more carefully than we did a couple weeks ago. Forward and reverse processes, what we mean, mostly kind of notational, but also review what information statistics are, symmetric and asymmetric, and when you scan a process in different directions. Then we're going to introduce forward and reverse epsilon machines that correspond to those 2 different scans. Talk about ways of measuring different kinds of irreversibility, or reversibility if you like. There's a way I kind of look at this in terms of the joint process lattice when I get confused. I actually have sort of complicated joint distributions over infinite variables of observed symbol and now forward states and reverse causal states. And so this is going to be a little roadmap so we don't get confused. Everything we're asking is actually a question about this joint process lattice, some conditional joint distribution. It usually turns out to be. And then I'll go through how to, when we reverse time, how we reverse a given epsilon machine. Think of it as a generator that generates the process in forward time. How we can, starting from the machine, reverse the machine and calculate the reverse time epsilon machine. See if we get through it. It's just a fair amount to cover today. Not, given what we've done, shouldn't be too difficult, but first part's just some kind of review. Again, just to set the notation, we're by infinite chain of random variables, past and future. And we look at blocks from time to t going forward L steps, or past blocks that come up to the length L, that come up to but not include time t, and our objects of study again, and processes that are distributed according to this huge bi-infinite joint distribution. Okay. Which the goal here is to get around using that by building models. Okay, so what we've been doing, so we're just going to recast what we've been doing, basically add little plus signs so we can keep track of this choice of scan direction. So what we've been doing, and it was done implicitly, even on the previous slide, on all the previous slides, I just wrote down an index on the random variables. Okay, and we just assumed, oh, okay, that was time. And we had the index increase by 1 each time we advanced. Okay, so but now we're going to call this, what we've been doing, not just the process, but the forward process, right? And I'll call that calligraphic P plus. And it's distributed according to the joint distribution over this scan direction. Okay, and we have various quantities, of course. We have the forward entropy rate. We talked about this a little bit, h mu plus. And that's the uncertainty in the next symbol given the semi-infinite past. But now we have to talk about the reverse process. So I'm still sort of giving you this lattice of variables, but I'm telling you, I want you now to scan this way. So there's a little bit of an issue, and I'll probably at some point misstate things. Human beings are very bad at binary logic. I'm one of them. So do I call these different variables and order them with an index that increases from left to right? Or do I talk about the original variable and then have a little variable accessing function that decrements when I go through? Your choice, but yeah. Okay. So, but the idea is absolutely simple. We're going this way, right? Right to left, we scan them. So we have this reverse process, and it's just simply p minus. And I'm going to sometimes use another variable y to make this distinction, where y is just simply the indexing through x in the opposite direction. Mostly, I'll write things in terms of this because then the contrast between left and right scan will be clearer. But sometimes the points we're making, it's handier to use Y. I mean, for example, if I want to define, I have a process over Y, I'm not telling it what direction it is. I say, oh, it's got an entropy rate. That's in the Y variable, I'm predicting the next symbol giving its semi-infinite past. But that was X's future. So I can write it this way because that's just applying the definition of H mu to this given process. But no, I know it's the reverse of something. So this Y notation turns into this X notation down here. Right? So the reverse entropy rate of P minus is the uncertainty in, call it the current or previous symbol given the future going forward. But that, from Y's perspective, that was its past and next symbol. Okay. Yeah, and there's a little bit of contrast here. Because of the way we define past and future, the future starts at t and goes forward. The past ends at t minus 1. It does not include x of t. There's just a little shift by 1 here. Just a definitional thing in the indices. Okay, so we played this game before. If I have these, I have a process. And it's sitting in my computer memory, and I can choose to scan it whichever way I want. So in which direction is a process more unpredictable, namely would have larger entropy rate? Well, we already went through this, right? Neither. In fact, the forward and reverse entropy rates are the same. So if I'm predicting or retrodicting, the average error or surprise is just h mu, and I'll probably, most of the time, just drop the plus and minus. And we went through a couple weeks ago the derivation of that. Pretty straightforward, mostly just an application of stationarity, right? So we look at h mu plus, that's the uncertainty in a current symbol given the past. We write this out to be careful. Now we're just going to condition on finite length pasts and put the limit out in front to give well-defined quantities, or obviously well-defined quantities. this uncertainty in the next symbol given the past, as we know, we're talking about block entropies. We can write it down as the two-point slope, or the difference between two block entropies. A block of length L plus 1 and a block of length L. That's just the information identity. Then we can shift these guys around, particularly this one, go the stationarity up, so this first symbol is times 0. The block entropies are the same if I shift it forward 1. Then I just substitute that back in here. So now remember, this kind of little rule here. If to get from the block entropies to the conditional, there's a variable that's left out. That's the one that is conditional. We're conditioning on this block, so x0 doesn't show up here. But what I've done now, I've shifted this up. So this goes from 0 back to minus L plus 1. This one goes from 0 back to minus L. Now, x sub L minus 1 is left out. Therefore, by that kind of heuristic, but it's just an information identity, I can, the difference between these two blocks is this conditional entropy, the uncertainty in sort of the earliest variable given the following L minus 1 symbols. Okay. So, well, I'm just going to get rid of these L's here. I'm just going to shift them by L. So now I'm back down to shifting x L minus 1 to x at time minus 1, shifting everything here. Stationary allows me to do that. But that is, of course, just when I take the limit, that is the uncertainty in the previous symbol given the future. Or, again, if I write it in terms of y, all I did is I've recovered exactly the definition of h mu minus applied to the reverse process. So just a little index gymnastics. Right, I start with this variable conditioning on this past. I write in terms of two block things. I shift the block over, and now I'm looking at this random variable here is free, and I'm conditioning on its future. That's all that's happened. I just shifted things. Okay, so the result is that entropy rate's the same. Now, does the amount of information shared between the past and the future depend on the scan direction? We talked about that. They're the same. And if you remember, excess entropy is this past-future mutual information. And the idea, well, the proof is pretty straightforward. It's just that the mutual information is symmetric in its variables. So here's sort of going through a little more pedantically that observation. So excess entropy of the forward process is a mutual information from the past and the future. Okay, let me be careful. I'm going to go into the past, into the future, length L, and pull the limit out here. So this is actually a well-defined thing. Well, we know that the mutual information, just for its definition, I can swap the order of the variables. It's the same, symmetric. So I move this past over to here and this future over to here, right? But by the definition of the y variable, this future is y's past, and that x's past is y's future. Again, index in gymnastics. Take the limits, then that's the mutual information between y's past and y's future, which is just the excess entropy of the past process. This isn't deep, it's just gymnastics with the indices. Keeping track in your head. Whose time direction we're talking about. Okay. So, entropy rate, excess entropy are symmetric in time. They change of scan direction. And if there was some statistical temporal asymmetry, you couldn't use them to detect this. So now does the stored information differ? And to do this, to answer this question, right, the stored information, the information we need to store from the past to do optimal prediction at rate h mu. To talk about that possibly changing, we need to talk about the epsilon machine of the reverse process. Okay, so first, just notation again, mostly just putting pluses and minuses on things we're familiar with. So we had this bi-infinite chain array of variables. We're scanning with the index increasing. And now the causal states, the analysis we get out of that by using the predictive equivalence relation, we're going to call the result the forward epsilon machine. M plus. Then we have this now just rewritten equivalence relation. We're going to call it twiddle plus to make the distinction. Right? We're grouping histories using the epsilon function. We group them so that the futures look the same. We're going from the given forward process and then sort of modding out by this equivalence relation. The resulting equivalence classes are the forward causal states. And we have all of our various complexity measures. I have the forward epsilon machine. There are things we can calculate. Right. The state averaged uncertainty in the next symbol, that's the entropy rate. Well, that would have been h mu plus, but we just argued that's the same thing, so drop the plus. We have the statistical complexity, something with the Shannon information in the causal state distribution with the forward states. Okay, and then we have the difference between state information and the observed mutual information. Remember, that was this mystery wedge, which we'll come back to several times, and even next week is going to be pretty much analysis of this. This what we call the crypticity, and there's a forward crypticity. It was that funny thing in the information diagrams where it was the given a future, our uncertainty in the current state. In this case, the current forward state. Okay. Similarly, for the reverse scan now, we have twiddle minus. So we have this, we're grouping futures to retrodict the past. Right? We put futures together when they give us the same reverse morph. I just sort of wrote it out here, right? So this is a future. We're conditioning two distinct futures such that the distribution of the pasts is the same. Then the result are these equivalence classes under that equivalence relation, the reverse causal states, and we also have the transition matrices, we call it, just like we did with the forward process, but scanning in the opposite direction. So that's the reverse epsilon machine is M minus. And we have our quantities. So we have what we might call the retrodictive entropy rate. We're using futures to predict the past, and certainly the next symbol, scanning in the reverse direction, but that's h mu. We have the size of the reverse epsilon machine, c mu minus, just the Shannon's information over the reverse causal states, and similarly we have a reverse crypticity. And all these quantities are going to come back and help us kind of get some sense of how to describe a process in a kind of time agnostic way. So this is the uncertainty in the reverse causal states given the pasts. Okay, so to try to put these things together, hopefully to make some kind of sense, we have our favorite information diagram roadmap. So this will be the past. So first we'll just talk about the forward process. So this is all familiar, except I'm relabeling things by putting pluses. Okay, then we have, right, so the past, the size of the past is, in the information diagram, it's actually the entropy of the past. Then I just put in the yellow circle. That's a subset of the past. This is the state information, right? The forward causal states are defined in terms of the past, so whatever information they contain is part of the past. Okay, and then the size of that is the forward statistical complexity. And of course we have the future. And then, for example, we're doing prediction, right? We're sort of looking at the uncertainty in the future given the past. So that's this red wedge here, right? Again, if you remember the way information diagrams work, I have the entire future, and then there's that part of it which is determined by the past. So I subtract that out. That's conditioning, and what's left over is what's uncertain about the future given the past, which I subtract out. Then the overlap between the past and the future, as we well know, that's the excess entropy. Right? That's just this piece here. The excess entropy is contained wholly in the future and wholly in the past. It's shared, that's what's common. Well, if it's wholly contained in the past and future, that means it's also contained inside the statistical complexity, the state complexity. Right? So we can now think of that as the mutual information between my knowledge of the current forward state and the future. I think we argued before, this uncertainty in the future condition of the past actually is actually well behaved. In particular, we can condition on the causal states because they're basically proxies for knowing the past, except sometimes they're finite when pasts would be an infinite set, so that's handy. And then we argued that, oh, well, actually, if I were just looking one step ahead, that would be the entropy rate. In fact, it factors due to stationarity into a product of these single symbol conditional distributions conditioned on the current state, which is then just the sum of h mu at every step. So this wedge is actually very well behaved here. We know how it scales. So that I've been a little bit improper here putting down these entropies of semi-infinite chains of random variables, typically just infinite. So the diagram is technically wrong, but now actually this red part scales well. So we can think of this future uncertainty is actually, once we know what causal state we're in, every time we go to one step longer future, we're just adding another h mu. That's our net uncertainty. So the way I think about this is that this red circle is that there are actually swaths here of area or size h mu. So it's sort of laminated or foliated. Every time I go from futures of length 1, length 2, length 3, I'm just adding on a new strip of area h mu. Okay, so that kind of gets rid of something that was actually kind of a technical number. I mean, it's intuitive what we meant, but now we can be careful about that. Okay, so now what about this? Okay, so this is now, here's the past, and now we're going to take out state information. So that's this green wedge here, and that's the size of which is uncertainty in the past, given the forward causal state. Slightly strange quantity, but there we have it. The diagram puts it up there. We have to acknowledge exists. And we just finally have this last piece, the mystery wedge, what I was just calling the forward crypticity. This is the state information minus the future. So at least graphically, this quantity makes sense. Maybe it's slightly bizarre to think, oh, what state am I in? What forward causal state am I in? Given that I know the future. So there can be some uncertainty. Same futures can lead from different causal states, so there can be some uncertainty. So anyway, so this wedge here, that's this crypticity. Again, the way to think about it, it's just the difference between C mu, statistical complexity, and E. Right, the handy interpretation of this, if you don't look at this maybe sort of confusing conditional entropy, it's just the difference between the internal state information and the past-future mutual information. It's kind of a measure of how hidden the process is. There's a kind of a superficial view. Just E was the past-future mutual information we get from statistics of the observed symbols. Now we've got a process that has a lot of internal structure, has a lot of state information. Okay. The crypticity controls that difference. All right. Now, just reverse everything, and then we'll compare. Okay, so now we are the Y process. So we're now trying to retrodict the past given the future. So here's the future. Here's our past. Now we have the reverse causal states, which are formed by grouping futures such that they do the same job at retrodicting. So this purple circle represents the reverse causal states, and the size of that is the statistical complexity. We have this piece over here, large, I've drawn it in green, which is the uncertainty in the past given the future. But that's exactly what Y is trying to do. It's trying to retrodict its past. So that makes sense. That's sort of the goal. E hasn't changed, right? It's symmetric. But we can also think of it as the mutual information between the past causal states, reverse causal states, and the pasts. Same argument we gave before shows that this green wedge, once we have the causal states, which I take the past and hack out that piece, then I'm actually retrodicting at the optimal rate. And so this green part is also foliated with, as we go to longer and longer words, with slices of size h mu. This red wedge here, for any kind of stochastic process, there'll be some uncertainty in the futures given what past causal state we're in. And then we also have the reverse crypticity. So, uncertainty in the current reverse causal state given the past. I guess I keep flipping time, making sense back and forward time and coming back here, but all perfectly symmetric. I just changed. Plus, minus, reverse the diagram. Okay, so we're actually getting pretty close to starting to understand pretty much everything there is about stationary stochastic processes here. We have this sort of epsilon machine view of the process's information diagram. So just going to summarize, we have E, which is shared between the future and the past of the process. We have the two different state informations here. They both contain E. The difference between the shared information and the past complexity or forward complexity, that's controlled by the reverse crypticity, and opposite statement for the forward crypticity. And then we know how these things scale here. So, in particular, we know that, right, if we take the future and condition on knowing the forward causal states, we know that these, the purple and red, they scale as LH mu. We're doing optimal prediction once we know what causal state we're in. And the same thing is true by a symmetric argument that the yellow and green wedges, this piece here, when we're retrodicting, as soon as we know the reverse causal state, as long as they have that information, then these two areas together are scaling with LH mu. So there's a lot we understand about this picture, information diagram picture of process. So what I'm going to do is focus in on these two wedges here. They're actually sort of critical to thinking about how hidden processes are. So these two remaining mystery wedges, right? This is one way to think about it, is if we're doing in the predictive mode. This is so I'm trying to predict, but then given that I know what current causal state I'm in, I'm uncertain about the pasts that led to me. Or if I'm in Y's case, I'm retrodicting. I'm uncertain about the futures that led to my current reverse causal state. So there are a few things we can say about these, just to kind of drill down a little bit. Just bringing these two results together. So what are these quantities? So let's go into the predictive mode. Well, you can show that it actually scales linearly after we subtract off the forward crypticity. So basically, this is just saying, just relating the crypticity to how the crypticity and this other piece scale. So we're trying to figure out what's going on out here. Well, we've already defined this, and we know that both of them together go LH mu. So it's just simple arithmetic to show that, again, so, just putting it the wrong side. Sorry. Just stop me. These are the forward states because they're part of the past. Okay, right. So I'm talking about this right here. So we know that this piece here plus this piece here scales like this. Right, send these two things out. It's just basically just trying to predict L steps ahead. You can look at the reverse causal states. I just sort of take that out, and then we get the scaling as h mu m. Okay, so just simple consequences. Same thing in reverse. Now we're trying to retrodict in some sense, but then we're looking at the uncertainty in the futures that lead to the current causal state. The same sort of scaling relationship here. Basically goes linearly after we subtracted off the reverse crypticity. Same argument. So at least we know something about what's going on here. It's not this wedge here we just analyzed, and the one on this page, the red, are sort of, they behave well. Not a surprise because we know together they scale LH mu. Together they scale LH mu. Because in either case we have the forward reverse states that are giving us the context we need to do optimal prediction at error rate h mu. Okay, so that's pretty good. I mean, we've sort of identified all of the pieces here. Maybe there are some issues about building up intuitions for these things, but we've got forward state complexity, reverse state complexity, shared execution user information. Crypticities correspond how hidden the process is, the difference between the state complexity and E, and then this outer wedge, which in the past I've been denoting as some sort of ill-defined infinite, semi-infinite chain of random variables. This actually scales quite well. Okay. So all of these quantities are really just questions about a joint process. And there are a number of different kinds of joint processes we could consider. One is just, now that I have a presentation of a process, they have states. And the states, there's some internal state process that the model implies. So we could talk about the state, observed sequence, state symbol joint process where the realizations are just pairs of state next symbol, state next symbol. We've just refined that, so we have two other kinds of joint process. Well, actually, it's the same as before. Before we were doing this, now we can talk about the joint process between forward states and symbols, or reverse states and symbols. But really, we're now going to be asking questions about how the forward and reverse processes are related, going a little bit beyond the information diagram. So really what we're talking about is this joint forward state, reverse state symbol process, where the events are current forward state, current reverse state, and symbol observed. So how are we going to think about that? So here's just some kind of a roadmap or guidebook. So this is what we have to deal with, right? These are the observed symbols, and we make this distinction between the past and the future. Everything up to this point has been talking about these forward causal states, right? So if I'm at this causal state at time 1, then this past is a member of its equivalence class. So 3, this past has its equivalence class. Also, everything I've been doing works in reverse, right? If I'm now going this way in the reverse process, looking at the reverse states, I'm down here at time -2, then there's this particular future is in the equivalence class twiddle minus of that reverse causal state, and so on. But anyway, stepping back, everything we're asking about is a question about this lattice of random variables. And this also says why it's a little bit complicated and confusing. But if you get confused, just write it down and figure out what you're conditioning on and what variables you're uncertain about, and it'll become clear in this. That you can even print this out from the slides and color things in as you're doing your homework, just so you don't get confused, right? I mean, you can tell, struggling a little bit to try to be careful when I'm saying forward and reverse. It's a little bit tricky. But if you lay it out here, you know, it's like a spatial lattice. Don't even have to worry about time, right? It's just a spatial lattice. In fact, these could be configurations generated by some spatial system like the cellular tile that we studied. And then there wouldn't be this issue of forward reverse. It would be left and right scan, and maybe some of the prejudices we have about time wouldn't be confusing. So, for example, so the exercises I'm suggesting in this. So if we have some quantity like this, I know my current forward causal state, and I'm uncertain in the future. Well, this is the canonical quantity for prediction error, right? I got my current causal state, and then there's some future leading from it. Same thing when I know the reverse causal states, and I'm trying to retrodict the past. Current causal state trying to retrodict the past. And I can do strange things like try to retrodict the past given the current forward state. At least on this diagram, again, just a set of random variables without this sort of semantic interest and confusion that we get. Same thing, using reverse causal states to try to predict the future. Okay. Why would you do such a thing? Well, it turns out these quantities are related to the crypticity, so that's why we need to sort of lay them out. Well, in fact, to be more correct about that, right? The forward crypticity was the uncertainty in the current causal state given the future. So there's some particular future you see, and now, given that knowledge, how uncertain am I in the forward causal state? Reverse crypticity is uncertainty in the current reverse state, I got to this way, using futures, in the past. Uncertainty in the past. Okay. And so on. I mean, you can ask all sorts of questions. In fact, we're going to end up today not talking about the observed symbols at all, but in fact talking about how the forward causal states relate to the reverse causal states. And that's going to be a key step that we're going to develop on Thursday to give what is basically a time-agnostic picture of a stochastic process. And let's just calculate all sorts of things. Okay, so sort of one consequence of all of this, perhaps at this point it seems like we're flogging a dead horse, is that there can be statistically irreversible processes, namely those with different statistical complexities. So, just reviewed that the entropy rates are the same in both scanning directions. Past-future mutual information or excess entropy necessarily by definition is time symmetric. But the stored information, statistical complexity, can be different. So now how are we going to analyze this? So I gave an example before. Today we want to actually calculate this, that the epsilon machines needn't be time symmetric. The forward reverse machines needn't be the same. And I say I just changed arrows. From plus and minus, I just changed the forward and reverse arrows. For forward and reverse machines, if the machines aren't the same, then the statistical complexity need not be time symmetric, although the statistical complexity is just a number. So this is the more detailed comparison you want to do. Here, I mean, the states aren't the same, or the transitions aren't the same, or both. Here, it's just a scalar. So you can have a large machine with low statistical complexity, and a small machine with, for it, relatively high complexity. Its numbers could be equal, so there's a little bit of, but it's a useful quantitative way of talking about identifying irreversibility. So the example I gave was the Smith-Arevich parameter setting in the logistic map. Remember, the Smith-Arevich parameters, the logistic map give parameter settings where the distributions on the interval are nice and well behaved. In particular, the iterates of the maximum are periodic, therefore we only have a finite number of delta functions, so they're nice, well behaved. Unlike the typical parameter setting in the chaotic logistic map where you have an infinite number of delta functions. Anyway, so this particular one is where the iterate of the maximum is periodic after 4 iterates. And then you can use that constraint between the logistic map to calculate exactly the parameters. Use a binary generating partition, and this is the example I showed before. In the quote forward direction, the direction in which I'm iterating the map, I get 4 causal states, no transient states. It's about 0.8 bits of per symbol per step of entropy rate, and about 1.8 bits of stored information. In reverse, we had 3 recurrent causal states, reverse causal states, and 1 transient state. Just a numerical check, our theorem. The entropy rate's the same, about 0.8 bits of uncertainty per reverse step, but then the statistical complexity is lower, about a third of a bit lower for this. Okay, so there can be, this is proof by just one example. There can be temporal asymmetry. Of course, one question is, how typical is that? And I think Ryan will talk about how often this occurs. It is very, very frequent if you randomly pick finite memory processes out of a batch of hidden Markov models. It becomes quite typical. I can't help but point out that this is often ignored in statistical analysis. So this, this is true for stationary processes. So even if we're in statistical equilibrium, there's a lot of discussion in physics about irreversibility and the second law and that kind of thing. But that's a different set of questions about the difference between microscopic time reversibility of dynamics and macroscopic properties. And typically people are talking about relaxing down to quote thermodynamic equilibrium. In some sense, the processes we're talking about are already in their equilibrium. They're called non-equilibrium steady states. And even there, we find that there's this asymmetry in time. So it's similar, but not the same thing as the discussion of irreversibility in thermodynamics. So it's a side comment there. So anyway, so what we've got here is that the stored information, statistical complexity, that we need to do optimal prediction, or retrodiction, depends on the scan direction. The asymptotic uncertainty we have, entropy rate is the same. The amount of information that's being shared between the past and the future, or the future and the past, is the same. But the amount of effort, the machine we need to reach the level of optimal prediction and to see that amount of shared information, that depends on what direction we're scanning. Okay, so this notion of reversibility that's involved in sort of physical discussion of thermodynamic irreversibility. So is the contrast, as I was just saying, between thinking about sort of microscopic detail dynamics. So here you should be thinking about a box of gas molecules banging around, picture in your head, hard sphere, elastic collisions. And the physics of that is if I change t to minus t, I get essentially the same behavior, different in detail because I just reversed time, but macroscopically it's the same. So, or the way it says, the physics is invariant under time reversal. So what would that mean here? So if we take the observed sequence to be a microscopic realization in this sense, what would it mean to reverse time? Well, so if we saw some word of length n like this, then reversing time is, and I'll just denote that, if I start with a word and I reverse its direction, well, that's going to be a new set of symbols for this y random variable, where I'm just going to swap the ordering here. Start from 0 to go to n. Now this is going to go from 0 to n in the y variable, or in the x variable from n back to 0 on x. Okay, so we can say that, define a microscopically, in this sense, microscopically reversible process is when the forward and reverse processes are the same. So what does that mean? It means, right, process is defined in terms of what words occur and their probability. So I mean both of those things are equal. So if we start with, say, the forward process, and we've got some word that occurs in forward time, then when we reverse it, that should occur in the reverse process, but then it should also be, its probability should be the same under the forward distribution. Okay. So here I'm using the forward processes distribution to compare. If I see a particular sequence this way with probably 0.2, I reverse the sequence. That also has to occur in the forward process with probability 0.2. Then it would be reversible. Yes, time semantics again. Okay, that's a very detailed view. In fact, you'll see it's kind of very restrictive notion of reversibility. What we're going to mostly be talking about is this kind of higher level thing, namely talking about processes that are causally reversible. And what we mean is just that these forward and reverse stored informations or statistical complexity are the same. It's a little bit of a coarse graining. What we really should be talking about is whether the two machines are the same, but just so we have something quantitative, we're going to define causal reversibility as when the statistical complexity is the same. So note that this previous notion of microscopic reversibility implies causal reversibility. Namely, if the forward and reverse processes are the same, well, then their machines are the same. If the machines are the same, then their statistical complexities are the same. The opposite isn't true.
Can you get the same machine out of different processes?
How do you mean different processes?
Well, you write down, right, that the P plus equals P minus, right? So your word distributions. Right? If your machines are the same, don't they generate the same word distributions?
Yeah, exactly. No, this is not deep. Yeah. Right.
So there's no way to get.
Right. Exactly. Yes. Yeah. I see what you mean. Yeah. Right. Whereas we're sort of, I try to emphasize in here this measure of causal irreversibility, just the difference between the forward and reverse statistical complexities, and it's just a nice crude measure of a time asymmetry. In the case of that Misarovich process on logistic map, that was about a third of a bit. Different models, if you will, of forward and reverse time you needed to do optimal prediction. One consequence is if you have a process that's causally irreversible, so we have a positive number here, or negative, just not zero, it means that complexities aren't the same. If the complexities are different, then the machines must be different. The machines are different, and the processes are different. So you can't go from causal irreversibility to microscopic reversibility. It must be microscopically irreversible. So anyway, this notion is much coarser. Okay, so now I wanted to show how the crypticity is sort of controlling reversibility or irreversibility. Kind of using this language to talk about the results we just had. So again, our forward crypticity is uncertainty in the current state given the future. Reverse is uncertainty in the past causal state given the past. Okay. So if this causal if we have a causal irreversible process, that means that these crypticities are different. So how do we see that? Well, either crypticity is just the difference between its forward reverse stored information and E. So E is symmetric in time, so the same across these two things. Thus, if it's causally irreversible, the statistical complexities aren't the same. But since E is the same, it means the crypticities are different. So I'm just trying to emphasize that crypticity is controlling this notion of irreversibility. We've been thinking about trying to do retrodiction with forward states, right? That sort of showed up before the information diagram, right? There was that wedge that was hacked out of the past, the forward state information. Okay, and so it showed that was scaling this way. We just scale just like the sort of past predictability scales. It's h mu l when we had reverse causal states. But we just had to subtract off the forward crypticity. But then that is, again, just the difference between C mu and E going in the forward direction. So what we see here is that if this wedge is positive, that can only occur, well, it's typical, as I argued, then given this relationship, there's a constraint on the lengths that we can be looking at. So just kind of work this through. And it's really just this relationship can only hold when L is larger than, so the smallest integer larger than the ratio of the crypticity over the entropy rate. And this is something called the cryptic order. So in other words, we start doing good retrodiction with the forward states when we go L symbols into the past. So next week, Ryan's going to talk about how to calculate, we'll give you some more interpretation of this. Here I'm just kind of laying out an interesting question here, and a constraint on this retrodiction distance. So another observation is when we think of the information diagram, there was that outside wedge, right, the past given the causal state information, forward causal state, and we add back in its statistical complexity. Well, we know that thing has an asymptote that eventually starts scaling like E plus H mu L. Right? That was just from the information diagram. So we have this quantity. In fact, I should probably, instead of equal here, what I should be saying is at some L will start looking like. So think back to the information theory in the winter quarter, where we were thinking about how the block entropy, we analyzed how the block entropy came up to that linear asymptote. But now, we're also concluding that the block state entropy has a similar asymptote, just by looking at the information diagram motivated scaling property. And that's going to be a critical thing. Next week, we're talking about the crypticity and what this sort of cryptic order is, and also the Markov order of the processes too, right? The block entropy, when it finally reached that E plus H mu L asymptote, it was sort of an indicator that we could do good prediction. And the L's that would happen were associated, at least in order of our Markov processes, L would be R in that case. So we're going to look at other block entropy scalings, so block state entropy scaling and state block entropy scaling, as a quantitative way to look at how this crypticity comes about. Well, same sort of comments, maybe no surprise, going in the reverse direction. I won't go through the whole argument here, right? So now we're trying to use the reverse causal states to predict the futures that led to them, right? There's some ambiguity in the stochastic process about what particular sequences would lead to a reverse causal state. Same sort of scaling argument, and we now also have a similar kind of cryptic order, but going in the associated with how well the reverse causal states predict the futures that are associated with them. And they have the same kind of scaling. So their block, so future block, past causal state entropy and scaling as an asymptote E plus H mu L. And you can also argue that these two block state entropies are the same, just by a simple time shift, by reversing, thinking about the reverse process. Probably should use the Y variables here. So there's something about, even though there are distinctions between the forward and reverse epsilon machines, there is some scaling here when we're looking at these block state entropies that becomes equal. They have the same linear asymptotes. Maybe it's a little bit not too surprising because the entropy rate and the excess entropy were both symmetric in time. So that constrains, if I'm looking at sort of block entropies going in forward time or block entropies going in reverse time, their asymptotes are going to be the same. So, okay, just a few observations about basically the crypticity and how we're going to study it. But now let's get down to actually doing some calculations. Right? I've been talking about calculations. We'll do one calculation. First, some examples of what happens when you scan forward and scan reverse and do epsilon machine analysis. So we're just going to go through our favorite examples here. Just kind of a snapshot of 3 or 4 cases. So we have the even process, and it's familiar. Epsilon machine, 2 states. If I see one, I must see one. just sort of state some properties that we'll calculate next week. This is not a cryptic process. What's that mean? Well, one way to think about it is that C, mu, and E are the same. Past, future mutual information and state mutual information and state complexity are the same. Okay, so now what happens when we reverse this? So we'll see why once we go through the calculational method, but I just want to give you kind of a survey of the different cases that can happen. So it turns out the reverse epsilon machine, if I see one, I must see one. In fact, what I've done here, and I'm putting in the branching probability from state A and parameterizing it. I'm carrying through the calculation, including that parameter. So these are sort of exactly the same, even as we vary P. From 50-50 to whatever, right? So the reverse machine is the same. Since it's the same, well, it's also not cryptic. Its excess entropy and its complexities are the same. It's microscopically reversible, right? Because the machines are the same, therefore the process is exactly the same. So if I see a word in forward time and reverse it and ask under the forward distribution, do I see that word and what's its probability? It'll be equal. Or the other way to say is if I see a word this way, it has a probability, I'm going to see it scanning the other direction with the same probability. Causally reversible, completely symmetric in time. Okay, so that's one case. Maybe in some ways, oddly, the even process are the least interesting. It's kind of, oh, okay. It's the same, not temporally asymmetric. Golden mean process. This one is cryptic. It takes a little calculation to see that, but we'll just take that as a statement. Now, what happens when we reverse the golden mean? Well, your intuitions might be, it just has this one restriction, no consecutive zeros, and that shouldn't change if I look at the other direction, no consecutive zeros. That would be correct, although the golden mean turns out to be a little bit subtle, and we'll go through the calculation for that. Pardon me, you will go through the calculation for this in the homework. So if I reverse it, I get the same thing, like this. Okay, if I see a 0, I must see a 1. So kind of like the even process, although it has this crypticity property, there's a difference between the mutual information, the observed information, and the state information. It still is causally reversible and also microscopically reversible because the epsilon machines are the same. So the crypticity doesn't completely drive this irreversibility, right? Like just the previous example, we had 0 crypticity. This one had positive crypticity, and they're both kind of trivially reversible, both microscopic and causally reversible. But we'll see when we calculate the reverse machine on Thursday for this, I think. The golden mean case is interesting and distinct from the even. Simple case, periodic period 3 process, ABC. So ABC, ABC, ABC. Well, okay, we know how to reverse this one, right? ACB, 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 that's fine. It's not cryptic, right? E is log base 2 of 3, period 3. State information, uniform probability, that's just log base 2 of 3 bits, Shannon entropy. So cryptic, but it's microscopically irreversible. Why? Well, if I'm looking at the forward process, I can see AB. But under the reverse process, I never see AB. I see BA, I see AC, but I never see AB. Yeah.
Do you need an alphabet size larger than 2 to have microscopic irreversibility?
Oh, wait, let me think. Hold on. Yeah, that's one of those general questions that get me into trouble. Let me think about that. I believe that's true. But,
I was wondering, it kind of intuitively kind of seems like you need an alphabet size larger than 2 to get microscopic irreversibility. But, because if you just have like 0s and 1s, it seems like the only types of restrictions you can say are I don't see consecutive numbers of.
Right, but the trick is going to longer words in this.
Yeah, what about 0, 1, 0, 0, 1, 0, 0, 0, 1, and then repeat that.
Yeah.
hidden large enough of it.
Right, yeah.
It's different.
Oh, right. So imagine that you coded A in a binary way and B in a binary and C in a binary way.
Yeah.
Then it would be clear at the cluster level they wouldn't repeat, and therefore, as long as you didn't put them all 0, 0, 0, 0, 0, 0, if you made them distinct, I think. Good exercise. Excellent question. Good exercise. Yeah. But you have to look at much longer words than just single ones. Random insertion process. So this one, go from A, bias coin flip, and I'm going to stick a 1 in back here with probability 1, or B, we do another coin flip. So we're randomly inserting a bit 0, 1 with probability Q, and then returning to A. This guy's cryptic. Anyone want to guess what the reverse machine looks like? I wouldn't say it's obvious. So.
Just reverse the arrows, all the arrows.
Right. Well, we'll go through that, I hope. Maybe I should let's move ahead here because I want to show you the calculational steps. So here, it's 4 states. And I've actually done it in full generality with the bias PQ parameters here carried over exactly. So the whole family of processes is distinct. So 4 causal states. And it's a little harder, like, why is that not the same? It's easy to see in the ABC case. So, and then you can, of course, calculate because I've given this to you, you can go ahead and calculate the state distribution for the forward process and the reverse process in closed form. If you plug in them both being fair coin flips, then you end up with these numbers. So forward and reverse entropy rates are 3/5 bits per symbol, 0.6 bits. Forward, about 1.5 bits. Reverse, about 1.8 bits. So we have about a third of a bit of causal irreversibility, and they're not the same. Therefore, the process is not microscopically reversible. Okay, one more example, I think. Call this the butterfly process. There's a whole zoo of these things. These are all built into the Computational Mechanics and Python library, the machine library. I'll play with them. 5 states over 7-letter alphabet. Again, it's not something one's going to typically do by hand, although we did. Okay, so what's the reverse machine look like? Again, completely.
Is it really different?
It's really different. So there you go. So this, but then that's why having some computational tools helps with this sort of thing. And again, you can go through and calculate. The previous the forward example had uniform probability on the states, so Lattice through 5. Stored bits of information. We do this one. The reverse machine, it's about 2.7 bits. So we have about 0.4, half a bit difference in causal stored information. It's something we call a 2 cryptic. 2 is the order, number of steps you have to go backwards from your forward causal state to start doing good retrodiction. But anyway, it's about 0.3 bits forward crypticity. Actually, if I know this number, then of course I can calculate E, because E, the crypticity is the difference between these two things. And I just calculated state complexities are easy to calculate given a presentation. I calculate the crypticity, then I just subtract that off, and I now have a nice analytical estimate of calculation E. And then from that, since the reverse crypticity is the difference between the reverse state information and E, I can calculate the reverse crypticity. It's about 0.7 bits. So these things are all related. In this case, we just had to calculate this quantity first, which we'll get to with Ryan. Anyway, this is just a list of cases. Even golden mean, the ABC process, random insertion process, and butterfly, and basically anything, well, with some constraints can happen. It can be microscopically and causally irreversible, cryptic, or cryptic, microscopically irreversible, causally reversible, not cryptic, and so on. So lots of things can happen. And we'll show you some more interesting examples as we go forward. Let's see if I can, 10 minutes, get through this. So let's try, make a Boy Scout try here. Okay, so there's sort of two questions in all of this. How do we calculate a reverse machine if I give you the forward machine? Right? I mean, I can give you a machine. It generates the forward process. Presumably you can reconstruct by looking at the process itself and get the reverse machine. But is there a direct way of doing this? Also, it will turn out that we would like to relate the forward state process with the reverse state process. That's going to be key to calculating a number of quantities, including the excess entropy in closed form. So the answer is pretty straightforward, and since we did all the work last week with mixed state presentations, what we're going to do is start with the forward machine, reverse the arrows. Great, that was easy. Problem is, that can be non-unifilar. Well, okay, we reverse the arrows, we actually have to renormalize the machine so we have a stochastic process, right? But that can be non-unifilar, so then we use the mixed state operator to calculate the mixed state presentation of the normalized reverse machine. And then, like I was emphasizing before, we then have to, the mixed states may not be the causal states, so we have to minimize sometimes. Okay, so we got about 10 minutes. Let's see if I can get through. I don't think so, but we'll try. We'll try. And then I'll maybe fix it on Thursday. Okay, but just so you can kind of see, it'll kind of wash over you in 10 minutes. Okay, so the random noisy copy process, that was the one of the examples we used last week when we were talking about the mixed state presentation, so it should be a little bit familiar. This is actually going to fill in some of the numerical details. So we flip a coin from A, we go to B on a 0 and C on 1, and then in either case we always return back to A on the next time step. It's just kind of a noisy period 2, except when we're coming back from C, we flip another coin with bias Q, come back to A, coming back from B, we generate a 0. Okay, so we have three states, so that's the forward presentation, 3 states, and we can just directly write out from the diagram the 2 symbol labeled transition matrices. We go to 140. Oh, yeah. Okay. So I'm also recording my lecture. Sorry. Yeah. I've had little eyes peering in for the last 5 minutes. It's like, all right, let's deal with it. Okay, sorry. Okay, so we have the symbol labeled transition matrices, and we can calculate the state probabilities, asymptotic state probabilities. Fine. So now what we're going to do is run the machine in reverse. How do we do that? Well, the first step is trivial. We just reverse the arrows. That's the same thing as essentially taking the transpose of the matrices. Okay. But then we end up with the probabilities of transitions leaving a state not being a normalized distribution. In other words, the rows in the transition matrices aren't normalized. So the trick to constructing a stochastic process for the reverse direction is to form this guy here. So tilde, or hat here, I should say tilde, is the transition matrix for the reverse process. So what we do is, right, so that's the, in forward time we go from state R to R prime, we want to form essentially the transpose, but with one normalization. This is the probability that I started in the forward presentation. I started in the next state and coming back to the previous state, seeing a symbol. So that's basically just the symbol labeled transition matrices transposed, but then I normalize by the state probabilities for those 2 states. And then if I just want to look at the internal Markov chain processes, I just, as usual, sum over the observed symbols. Okay, so that said, here's what it looks like. It's the random noisy copy. So now oh yes, okay. So these 2 matrices are now the symbol labeled transition matrices for the reverse machine normalized according to that calculation. It turns out that the forward stationary distribution is the same as reverse stationary distribution. Okay, so that's a handy thing. But now what we have, and I've written it out here, so now I've reversed the edges. Remember, A going in the forward direction went to B and C. Well, now I have these incoming arrows, and I just recalculated them. And same, A now goes out on a 0 to B, and on a 0 to C, or on a 1 to C. I recalculated the transition probability, so they all sum to 1 going across the rows. But it's now messed up because it's non-unifilar. So that's where the mixed state calculation comes in. Someone's getting a cell phone call. So now we have, so the previous presentation was the random noisy copy, forward direction, but then reversed and renormalized. So it's now a hidden Markov model again. Just reversing arrows doesn't allow that. And now we're going to calculate the sort of mixed state presentation, and so we're going to make this identification. In this case, it happens to work out that the reverse causal states, reverse mixed states, I should be, but they happen to be the same in this case, are the set of mixed states that are induced by seeing these words going in reverse time, right? And that's going to be the probability of our uncertainty in the forward states, given that we've seen these various words. Okay, so just like before with the mixed state calculator, where no words, words of length 1, words of length 2, that we see in the opposite direction. Okay. Or in the forward direction for the reverse machine. Okay. And we'll get transient recurrent states, and we're just going to ignore the transient states just to keep our lives simple. So we start with not seeing anything, lambda. Well, in that case, it just means that we'll have some mixed state that is the pi of the forward process. Okay. I calculated that out before. That's this guy. Okay, then we calculate the mixed state now, having seen a 0 or having seen a 1. So here are the expressions for that, and also the interpretation, right? So if here's this language thing, my uncertainty in the current causal state, given that the next symbol was a 0, or that's the same thing as using reverse presentation and having seen a 0. So then, and these are just the expressions. I'm just plugging the matrices we just calculated into the last week's mixed state update, right? We're updating the mixed state, having seen a 0. So we just calculate that out, and here's the, once all the mess settles out, we get this probability vector here, and this piece down here is just normalizing it. So it's actually a distribution, and same thing on having seen a 1. Work this all out. That vector. So that's the mixed state after having seen a 1. Almost simple. And so on. So we just keep going. So we keep extending with one more symbol to longer and longer words. And then we're curious. Again, we're thinking of this almost like the parse tree. We have these two mixed states that we just calculated, and we want to know where this one goes if I see a 0, 1, and where this one goes when I see a 0, 1. So that means we calculate out these mixed states, having seen 0, 0, 0, 1, 1, 0, 1, 1. And just kind of plugging things in here, we just have these same expression, or we could, of course, collapse these two symbol-labeled transition matrices to be the symbol-labeled transition matrix on a word of length 2. So let me not go through that. We're just plugging in here. And then you keep doing this, going to longer and longer words until the mixed states start repeating. Okay. And if it's a good day or the mixed state gods are smiling on you, that'll actually stop after a finite number of words. But it needn't. It's kind of a key point. Sometimes these things will blow up. So in this particular case, I mean, I'll just say it. You can actually verify it with the camping stuff, or if you want to do it by hand. For the random noisy copy, these two mixed states are the same on these two different words, conditioning on these two different words. So the machine sort of folds back on itself. And if we start seeing the same mixed state, that's the same condition we need to predict the future well. Therefore, we identify those, and they basically are proxies for future morphs that are the same. And we identify those states. So we end up with, if you do the calculations, you end up with 3 reverse states, calling D, E, F to be different. And you can say, well, if you're careful to track through the calculation what the mixed states correspond to in the original machine, you can see that, I'm leaving out the details, that the reverse causal state D, which we got turns out, through that, seeing that word, this corresponds to this mixed state, do the calculation, but then that means that D is really associated with being in the forward causal state C. Okay? Same thing with E corresponds to A, and it's really just this new state F that's a mixture. You're confused about whether you're in states B or C. Okay, so, and then we go through and calculate the transition probabilities. Sort of running out of time here, and more eyes are looking at. Right, we want to know if I've seen 0, 0, and I go to see word 1, 0, 0, how the mixed states get updated. And we gave the transition probability, also those mixed state resource notes go over the transition, the expression for the transition probability to go from one mixed state to another. And in this case, randomized copy, we can do this in closed form. So then we do this, after we have all the unique mixed states, namely unique reverse states, you just go and pairwise and calculate the transition probability. Tedious, of course, but then the result is this. So again, carrying everything through in closed form, we end up with 3 reverse states, but now new transition probabilities. So it's similar in structure to the forward process, but different in the particulars in terms of the actual transition probabilities. And if you look at this, we have 0 and 1 leaving here, we have 0 and 1 leaving here, 1 leaving here. It's a unified presentation, and we can go calculate entropy rates and statistical complexities. So they all make sense. So, as I hinted at the beginning, the mixed state turned out to be the causal states in this case, and that's not always true. So, so this happens to be the calculation we just went through. It is the epsilon machine of the reverse process. In general, what you have to do is you have to minimize the mixed states. The mixed state presentation is a unified presentation, which if you remember way back to when we were talking about the epsilon machine optimalities, if you have a unified presentation, it means it predicts the process, it describes the process. And in addition, its partition of pasts is a refinement of the causal state partition. The causal state partition being coarser and having fewer cells. So flip that around. So we have this unified presentation. So sometimes we have more states, mixed states, than are necessary. So you have to minimize. That's the punchline here. And when you're doing these calculations, it's just better to get rid of the transient states. If you're starting to calculate mixed states and you end up with a bunch of transients, most of the things we're calculating really just refer to the recurrent mixed states or recurrent causal states. So you can actually just get rid of that. And that will make the matrices that you're working with smaller. So, so then what you do is just then get rid of those transient states and then simply group states together in terms of the probabilistic equivalence, which would then minimize them, group the mixed states together, and then you'll get the causal states. So that's sort of the end of the process. Calculate out your mixed states. It might be too big. The set of states might be too big. You may have lots of transient states. Dump the transient states, and then minimize the recurrent states using essentially the predictive equivalence relation. You merge states when they lead to the same distribution of futures. Now, there's a little bit of a trick in this. If you strip the transients and calculate the mixed state presentation, that can also minimize, which actually now that we have the computation mechanics of Python software and we have software that does this for you, this is an easy next step to do. Just do it again. Okay? In fact, we're now sort of working on kind of a conjecture based on some recent work in regular theoretical computer science and automata theory that on the minimization of finite state machines, that if you reverse and calculate the analog of what I call the Nerode equivalent states and then reverse again, then you end up with a minimum machine. So in this case, we're currently working with, like I said, it's a much more general minimization algorithm for any presentation. Calculate the mixed states, reverse it, mixed states, reverse, and then mixed state again. And we believe that'll give you the epsilon machine, the causal states. But stay tuned. All the cases we tried, that works. But we haven't proved it yet. So anyway, one of the key things that we want to calculate Okay. So last lecture we were talking about the sort of forward process and the reverse process as if they were sort of separate processes. But in fact, when we sort of pointed out in that joint process lattice, we have questions that relate to the forward states and reverse states, for example. So one of the things we like to calculate is, in a sense, this joint forward-reverse state distribution. And it turns out the way we were calculating the mixed states, we were actually tracking all of this. So that's going to be the theme today. Start thinking, taking a step back and not just realizing that the forward and reverse processes can be different in terms of their statistical complexity, two different representations, but actually we're going to go in the direction of a sort of unitary view of any stochastic process that, in a sense, is sort of time agnostic. So rather than having this time always increases left to right or right to left or whatever, past, future, we'll end up today with a way of just talking about joint causal states for the past and future. Okay, so what we were doing in calculating the mixed states, right? We started, say, with the epsilon presentation, the forward process. We reversed it, normalized things to get a stochastic machine, typically non-unifilar, and then we calculated the mixed states to get the reverse machine. And then we want the epsilon machine, maybe minimize. Okay. In fact, this minimization process I just mentioned, the conjecture, is actually going around this loop once, starting with any presentation, not even the epsilon machine, going around once and coming back with the epsilon machine, the forward process. Anyway, so this is the commuting diagram that describes. And what we want to do is as we're tracking, right, so we have the forward causal states, we reverse this, normalize it, we still have the presentation states here, and then we calculate the mixed states, which are distributions of over these states. Well, in that calculation, we can track how the reverse causal states, which are now distributions of the forward causal states, how they're related. So if you think back to, and I'm not expecting you to remember, especially after 2 days, the details of the calculation that we did for the random noisy copy process, but let me just restate things. Actually, as we did this, we were keeping track of what we need to keep track of to talk about the joint causal state process here. Okay, so again, recurrent causal states, just look at causal states, that's asymptotic probability positive. If you remember, well, the forward random noisy copy process had states A, B, C, 3 of them. In this epsilon machine presentation, we calculated that we had 3 reverse causal states, and then last lecture we were talking about how to calculate these mixed states from those. But these mixed states were distributions over the original presentation states. So in fact, given that I was in reverse causal state D, and this guy, that really is the conditional distribution of being in reverse state D and asking, oh, what forward state could I be in? There's the distribution there. So in this case, what we calculated was, for this example, that basically states C and D are synonymous. Or we're in the same condition of knowledge about the future when we end up in state D scanning reverse or scanning forward, we end up in forward state C. So this is a one-to-one mapping. Same thing here. So I'm just actually rewriting the calculations we did, just reinterpreting them. Same thing in E, it was this mixed state. So there was no uncertainty. If I'm in, look at the joint process lattice, if I'm in reverse state E, I know that I'm in forward state A. So what was interesting was state F. There's some ambiguity here. So if I'm in reverse state F, there's some uncertainty. I could sort of look up in my lattice and see sometime the forward process will be in state B or C. So in a sense, trying to think about this joint process, we've already done the calculation. The mixed states are these conditional distributions. So if we want to get the joint distribution, for example, then we just calculate the asymptotic state probability for the reverse machine, multiply it times this, and that gives us the joint. That's just our basic probability identity. So we know how to track these things. So that's good. So now what we'll do is use this. to move in the direction of this more general time agnostic